Hello students. So, in the previous class we started with the integral aspects of vector calculus, and we started with line integral actually. So, I left off the previous lecture at a very interesting example in my opinion actually. So, today we will continue with the similar example. So, we were given a vector function, and we had to find out the line integral of this vector function f along this rectangle. So, we have assumed that the orientation is in this way. So, OA, AB and then CO or yes CO. So, now let me write these points A0 and then this is AB and then this is B0, all right. So, now on OA, so on OA y is varying, x is varying, but y is 0 because the equation of the line OA of the x axis is y equals to 0. So, on OA x is on OA our y is our y is 0, our y is 0 and therefore, dy is 0 and x varies from 0 to a, right. So, 0 to a. So, 0 to a, that is how x is varying. Now, on AB our x is a and therefore, dx is 0 because x is constant. So, dx is 0 and y varies from 0 to b, right. Okay. Now, on BC, we have y equals to b and therefore, dy will be 0 and x varies from a to 0 and on CO our CO x is 0. So, basically dx is 0 and y varies from b to 0, right. So, basically we have 4 smooth curves. So, and along all these 4 curves we have these 4 criterias. So, now instead of calculating the line integral of the vector function f along this curve C, so along this curve C, the line integral along the curve C1 dot dr plus C2 dot dr, C3 f dot dr plus C4 f dot dr will be same, because our curve C is actually the union of C1, C2, C3, C4. So, here we can write union of C1, C2, C3, C4, and from some of the properties from integral calculus or Riemann integral, this union can be transferred into a summation. So, it can be changed into a summation. So, basically integral over the union of the domains is equals to the sum of the subintegrals over each of these domains, all right. So, that is what we are doing here. So, integral over C1, C2, C3, C4, if you sum them, then that will be the integral over the curve C. So, that is the formula which we have used here, and we can call this line as our curve C1, we can call this line as our curve C2, we can call this line as our curve C3 and we can call this line as our curve C4. And we have to now evaluate these integrals separately. So, what is the value of the integral along C1? So, C1 f dot dr. So, C1 is where y is, let me go back. So, on C1 x is varying from 0 to a. So, on C1 x is varying from 0 to a and our f is given by this equation. Now, on C1 y is 0. So, dy is 0. So, when y is 0, this is 0 and when y is 0, so this term is 0. So, we basically have x square I. So, we basically have x square I plus 0 times j, and dr can be written as dxi plus dyj. Now, dyj dy is basically 0 because y is 0. So, dy is 0. So, we are ultimately left with I times dx. So, here we have dx times I plus 0 times j d. All right. And now, if we take the dot product, then this is basically x running from 0 to a x square dx. So, this is a cube by 3, I believe, yes. And similarly, we can calculate the integral c to f dot dr. So, here y is varying from 0 to b. So, I can write y is varying from 0 to b, and then x square, here x is a. So, x square plus y square. So, I can write this as a square plus y square times I minus 2 a y j, and then dot product with dx I plus dy j. So, what will be dx? Dx is 0, and this one will be, so 0 I plus this one is dy j. So, this one is dy j, and when we take the dot product, then this will be minus of 2 a y running from 0 to b y dy. So, this is ultimately minus a b square, and then similarly, if we integrate C 3 f along C 3 f dot dr, then this will be basically again y equals to b, and then dy is 0, and then we substitute x running from a to 0. We reverse the, and then we reverse the minus sign. So, since we are integrating, a is a positive number. So, we cannot so it does not make much sense if you are integrating from a to 0. So, it always has to be 0 to a. So, just do those formula changes. So, what we will get is basically this thing. So, we have x running from a to 0, f is our y is b. So, this one will be x square plus b square. So, x square plus b square times I minus 2 x b j, 2 x b j, and then this will be dx I plus dy j. So, dx is that one is fine, and dy is 0. So, we can write dx I plus dy 0. So, when we integrate, then this will ultimately give us or what we can do, we first change the formula. So, this will be a x running from 0 to a, and then we write the entire dot product. So, when we take the dot product, this will be basically x square plus b square times dx, because I will be gone. So, now we integrate this x square plus b square from 0 to a, and similarly we integrate. So, similarly we integrate the curve, the function along the curve C 4, and then you sum them, and ultimately we will obtain the answer. So, ultimately we will obtain the answer I, let us say, is equals to minus 2 a b square, and this is the required answer. So, here in this case, instead of having one smooth curve, we basically had how to say, a union of 4 smooth curves, and those 4 smooth curves actually needed to be evaluated. So, basically the line integral along those 4 smooth curves needs to be evaluated separately. We cannot do C in whole, we have to do like C 1, then integral on C 2, then integral on C 3, then integral on C 4. So, sometimes you might come across examples where the area, or sorry, the curve is actually composed of a parabola and a straight line. So, you basically have to divide your integral into 2 sub integrals. So, you first have to integrate along that parabola and then integrate along that straight line. All right. So, that is something I wanted to show you. So, of course, there are examples like that, and due to time constraints, we have to finish this course on time. So, we will move on to our next topic, which is basically surface integral and Green's theorem. So, basically what do we mean by surface integral? So, let us assume that this is our surface S in 3 dimensional space. So, I call it as S, and any integral, so it is like line integral definition. So, any integral which is to be evaluated over a surface say S is called a surface integral. So, basically what do we mean by is, so there is a very nice theory going on at the back, but we generally write it as in this way. So, when we are doing the surface integral, we usually denote it as surface integral over S f dot n ds, which can also be written as surface integral over S f dot ds. So, here what we actually mean is that this f dot n is the component of f along the normal n, and this ds. So, on the surface of this on the surface of this let us say this surface S, we basically have, this is our vector and this is our point P, this is our vector f and this is our vector or the normal n. So, this f dot n is actually the normal component of f at the point P, and if we the integral of f dot n then over the surface S. So, this is the integral of the function f dot n over the surface S is given in this fashion. So, this is just like a notation. So, when you will be given as, let us say, a vector function, and then from there you have to calculate the normal n, so that you can evaluate this surface integral f dot n ds. All right. Now, when we evaluate the surface integral, we have to remember certain ways that how we can evaluate. So, this is of course given, is given as an abstract definition, that what do we mean by this component of f, integral of component of f along the normal n over the surface S. But when we need to evaluate this, we need some kind of formula that will help us to evaluate. So, the formula is, you have to take the projection of this surface either on xy plane or yz plane or zx plane. So, depending on your projection, basically your evaluation will depend. Of course, the answer would remain same, it is just that the complications or I do not know, the way you solve the problem will depend on which plane you are taking the projection. All right. So, here we have f dot n. So, the first projection let us say we are projecting on xy plane. So, then this will be surface integral over S f dot n ds, which is surface integral over S f dot n dx dy divided by n dot k, right, f dot n dx dy divided by n dot k. So, this is what we get when we take the projection on first projection or projection on xy plane. Similarly, you can take the projection on the xz plane. And we can take the projection on yz plane. F dot n, sorry. x z. So, if we are taking the projection, so this has to be j, and when we are taking projection on y z plane, so this has to be I. So, the trick to on y z plane. So, the trick to remember these formulas is that whenever you are taking projection on a certain plane, so that will be in the product dx dz, and then the remaining axis. So, if you are taking the projection on x z plane, then basically y axis is perpendicular. So, you take n dot j. So, j is the unit vector along the axis y. So, we take basically n dot j. Similarly, if you are taking the projection on x y plane, then your z plane is then your z axis is perpendicular to x y plane, and therefore, you take n dot k. And similarly, if we are taking y z plane, then x axis is perpendicular to y z plane, and therefore, we take the projection we take the product as n dot I. So, it is a very nice and convenient way to remember these formulas. All right. So, now we will see how we can solve some examples. So, this is of course given in a bit abstract way. We will see how we can work out an example. So, let us start. All right. So, to begin with, so evaluate f dot n ds, where our function f x y z is y z I plus z x j plus x y k, where S is the part of the surface of the sphere x square plus y square plus z square equals to 1, which is in the first octant, So, here in this example, what we have is we have a given vector function f, and here we have to calculate the surface integral f dot n ds, and our surface along which we have to integrate basically, or on which we have to integrate is given by x square plus y square plus z square equals to 1. However, there is a small catch that we have to just consider a surface that is in the first octant. So, if you consider, let us say, a circle in 2D, then it actually has 4 quadrants. So, and in case of a sphere, since it is a 3-dimensional geometry, you will have actually 8 octants, and we have to limit to the just the first octant. All right. So, let us start. So, first of all, if we want to calculate f dot n, we have to find out n, what is our n, and unless you calculate this n, we cannot proceed any further. But we remember from the gradient, divergence and curl, that gradient of a function, or the gradient of a given, let us say you have the equation of a surface, then the gradient of that f equals to that surface is basically a normal to the surface. So, the gradient of f is actually a normal to the curve f is equals to some constant, or f equals to 0. So, basically a vector normal to the surface S is given by S equals to gradient of I do not know, phi, where phi x y z equals to x square plus y square plus z square minus 1, right. So, this is the required equation of the, or basically phi is equals to x square plus y square plus z square equals to minus 1. So, now and we do not have to write S here. So, a vector normal to the surface S is given by grad phi, and this grad phi can be calculated now. So, grad of x square plus y square plus z square minus 1. So, this is basically 2 times x I y j z k. All right. So, we take the gradient and that is what we obtain. Now, this is normal to the surface S, but n is the unit outward drawn normal. However, gradient of phi is just the outward drawn normal. So, we have to now calculate n cap. So, to calculate n cap, a unit normal, therefore, a unit normal to any point, to a unit point, to any point actually. So, a unit normal to any point x y z is basically n equals to grad phi divided by gradient of phi. So, grad phi is 2 times x I y j plus z k, and when we take square, so this is basically 2 times so 2 times x square plus y square plus z square. Now, x square plus y square plus z square is 1. So, this is basically x I plus y j plus z k. So, that is our normal n, and now we will take projection on x y plane. So, if we take the projection on x y plane, so this is our plane y, and that is the first octant r, because if you take the projection of first octant in the sphere, if you take the projection on x y plane, then it will be a circle in the first octant. So, taking projection, and of course, a vector perpendicular to this x y plane is the k axis, right. All right. So, taking projection of S into the x y plane. So, taking projection of S into the x y plane gives so this is basically our unit normal, and now taking projection of S into x y plane, it will be basically so our f is y z I plus z x j plus x y k, y z I plus z x j plus x y k, dot product with d x y d x y d I divided by n dot k. So, first of all, here I will write our normal, which is x y y j plus z k, and d d, and this one is basically so we have n and we have f, and now d s is basically d x d y divided by n dot k, right. So, here in this case what we will obtain is n dot k. So, this is nothing but so r is basically the r is basically our after projection the new area basically, or the new place where we are doing the integration, and here in this case if our n is k basically. So, n is the unit normal perpendicular to, so n is the unit normal and k is the given k is the vector perpendicular to x y plane. So, if you take n dot k, then this will reduce to just z. So, from here what we have is f dot n is, if you break the dot product, then this will be 3 x y z, and k will be n dot k will be basically n dot k will be basically z, right. And therefore, if I substitute everything here, then surface integral f dot n ds is equals to integral over r 3 x y z, and then times, this is basically times, it is not a cross product, dx dy, and n dot k is again z. So, this whole thing will reduce to integral over r 3 x y dx dy, right. And now, what we will do is we substitute, since we are in the in 2 dimensional geometry, and it is basically sort of like a surface this integral in the circle, this whatever you want to call, we basically substitute x equals to let us say small r cos theta and y equals to small r sin theta. So, basically we substitute x equals to r cos theta, y equals to r sin theta, and therefore, the required line integral the required surface integral, let us say I am calling it as I s, equals to I have r running from 0 to 1 because it is of unit radius, and theta, since we are in the first octant, then theta first quadrant, then theta will run from 0 to pi by 2. So, that I am writing here, and then I have 3 is here, x. So, x is so this is x is r cos theta. So, 3 r cos theta, and times this one is y is r sin theta, right. So, y is r sin theta, and everything is transferred to spherical polar coordinate system. So, we have r dr d theta. So, if you multiply this whole thing and take the term for r on one side, so this is r running from 0 to 1, this will be r cube dr, and this one will be theta running from 0 to pi by 2 sin theta cos theta d theta. So, we integrate this thing here, and then we integrate this thing here, and this will give us 3 by 4 times half. So, this is ultimately 3 by 8. So, we adjust half with 2 here, and then we do sin 2 theta and all that. So, this is the required answer. So, in this case we basically have to find out the projection of the surface on a certain plane, and just having to know the projection, you can be able to solve the rest of the example. We will solve some more examples on surface integral in our next class, just to make the concept clear, and then we will move on to volume integral. So, I will stop here for today, and we will continue with our examples on surface integral in our next class. Thank you.